Welcome to a video on bistable circuits. Okay, so in this video we will be looking at applications of a bistable, the working principle, the inverting and non-inverting bistable. We'll be needing both for the oscillators, then some limiting circuits, and then we will do some simulations. Okay, so application of a bistable is typically a trigger. Okay, and they have two triggering levels, not just one like the comparator have. The comparator is on or off either side of some reference voltage. So there is two trigger levels in a bistable. So this can be used as noise reduction, so that when there is a kind of oscillation around your reference level that you don't trigger all the time. Okay, so it's a bit of a buffer. Okay, so typical applications is square wave generators. So that is the inverting bistable, and then triangle wave generators, which is the non-inverting bistable. The bistable can also be used as a memory element. It remembers its previous state to determine at which level it will trigger again. So you will find these bistables in many digital buffers and inverters. I usually have a symbol on them that looks like this, and they are typically called Schmitt-triggers. Okay, not necessarily bistables, so it's the same thing. Okay, so the working principle. Schmitt-triggers use positive feedback. So with positive feedback and op amp, we are ensured that our output will always be saturated. So it will either saturate to the positive limit or to the negative limit of operational amplifier. Okay, so looking at the bistable means that there is only two stable states. So if you take a hill and you put a ball on top of a hill, it will roll off to either one of the two sides and remain there. And to move it to the other side, you need to insert some form of energy. Okay, so it will never remain on top, it will always roll down to one of the stable states. Okay, so the one side could be output being saturated positive and the other being saturated negative, and by putting an input in, you push this ball to the other side, and some other form of energy is needed to push the ball back to the other side. Okay, so the trigger levels of this bistable is very dependent on the previous input. Okay, so let's go to example. The sine wave is the input to one of these bistables. Okay, and you'll note that the output is at the high. Okay, the upper limit. We call that L plus. The lower limit is L minus. So this is the output of the op amp. So the first trigger here, the red one, the moment that this sinusoid reaches 1 volt, the high trigger, the output of the amplifier will switch to a low state. Okay, and that low state will tell the amplifier what the new trigger level is. Okay, so this signal at the input can go almost anywhere upwards and whatnot, but the moment that it breaches the lower trigger point here at -1 volt, the amplifier will switch again to a high output state. So the trigger level is back to the high trigger point. So it will jump between the high and the low trigger points of the two. The second example is a trigger point moved here just above 4 volts and the negative trigger point is just here below minus 4 volts. And the same principle apply. The moment that this sinusoid reaches this point, the output of the amplifier will switch to a low, and the moment that this point is breached, it will switch to a high. Okay, so the way that we describe this is the positive limit is VCC minus the amplifier saturation, and the lower limit is VE plus the amplifier saturation. Okay, now the trigger itself. If we have a look here, V out and VP, we can write this down as a voltage divider. Okay, and VP is also equal to V in. So this is the feedback factor of this amplifier is resistor 1 over resistor 1 plus resistor 2. That will determine the trigger points. Okay, so the moment that this input breaches the trigger, the output will change state and the trigger will change as well. And then the new trigger needs to be breached before the output changes again and we have a new trigger. So we will be flipping between the two trigger points as well as the two outputs. Right, then you can also apply offset to the triggers by adding a voltage source here where we had a ground point. Now, with the triggers and the output in mind, we can set up a hysteresis loop or the transfer characteristic. So let's focus on the blue graph here. So let's assume that our output is at a high or the positive limit. Okay, our input down here can be any voltage in this area above and the output will not change. But the moment that we reach 1 volt for our input, okay, so this is all negative voltages. The moment that we reach 1 volt, the output will jump down to this negative state. And then our input can be any voltage from minus 1 volt up to wherever without this thing changing states. Okay, so the moment that the input reaches minus 1 volt, our output will change back to the positive limit. Okay, so the trigger level is dependent on the amplifier output, giving us this hysteresis loop. So in short, we have a comparator with a triggering level at 1 volt and a comparator with a triggering at minus 1 volt. So this is basically a combination of two comparators with different levels. Right. If you apply offset, the only thing that happens is you move this hysteresis upwards or downwards. So the blue one is our typical one at 0 volts. Then if we apply 5 volts, we move our trigger upwards. This is nice when you're working with single rail applications so that you can move your trigger to wherever. Okay, so the typical trigger that you get in a TTL application will be sitting here at 2.5 volts, the center of this thing. Okay, so you need to move your trigger upwards with 2.5 volts. Note that the center is determined by the offset that you apply. So the center here is at 5. So for TTL, you're going to have to move it to 2.5 or whatever application you want. If we insert the negative offset, it moved that way, and its center is now at -1 volt. Right, the non-inverting bistable works a little bit different. So again, with a sinusoid, our signal will now start off at the negative, and the moment that our high trigger is breached, our output will go to a high. When our output goes to high, our trigger will move to be a low. So we need to breach this -2 volt level here for our output to switch off again. And the moment that this happens, our trigger changes back to being a high trigger point. Okay, so the output limits works the same. It is the feedback factor that is a bit different in this case. So this looks more or less like the inverting configuration of op amp, just our feedback is a positive. Okay, so we take superposition for point VP. So first we make V in a ground, and VP is then a voltage divider from V out towards ground, giving us our first term. And if we make our V out a ground and V in our input, we get a second voltage divider. But due to Vp being equal to Vn equal to ground and 0, we can get rid of this Vp, and your feedback factor will be minus R1 over R2. So this is the wrong way around in terms of an inverting amplifier for the resistor ratios. Okay, so the feedback factor is determined by these two resistors. Then, if you want to apply offset, you can just add it here on the negative terminal of the amplifier. And as a hysteresis loop, it looks like this. So assuming that our output is at a low, we need to breach the high trigger for it to go up. So this is a typical non-inverting configuration. And for our output to go to a low again, we need to breach this -2 volt point here, or our lower trigger. In terms of offset, applying a -2 will move it downwards to -2. Applying a +5 will move it upwards towards +5. And the standard again, the blue here in the middle. And that is it for the bistable itself. Now let's look at these limits. At this point, the limits is determined by the op amp itself and the rail provided. Now, the rail in a system is not always going to be stable, so we want our limits to be at values that we choose. So to do that and get VE and VCC out of the loop here, we can limit our output using Zeners. Okay, so for a positive output, we will see Zener voltage of diode 2 and diode 1 will be a diode voltage. Okay, so the Zener voltage plus 1 diode voltage. For a negative current, we will see Zener 1 and diode 2. So that will be our new limits. So having two Zeners like this, you can either have them at exactly the same Zener voltage, providing a symmetrical output, or you can have two different Zeners, making your output non-symmetrical. So you can have different positive and negative limits using different Zeners, but this will affect your transfer curve. Okay, so you will have different limits and different triggers. None of those will be symmetrical. Okay, with these limitations, you also need to add a current limiting resistor at the output of the op amp. And what current is flowing through this resistor will determine its size. So first, how much current will be flowing through the Zener to switch the Zener on and keep it on, how much is flowing into the feedback, and how much is going to any loads attached to this node right here. Okay, so resistor 3 you can determine with VCC minus VSAT, which is the maximum output voltage here, minus the limit that you set using the diodes, or you can do it on the negative cycle, but whichever yields the lowest resistor will be the correct answer. Okay, so this is to ensure that you have enough current being delivered to everything. If the Zener is not on, the output limiting will be useless. Okay, so always the smallest resistor of R3 to ensure that you have enough current for your feedback, switch on your Zener and drive any loads attached to this circuit. Okay, in terms of symmetrical and non-symmetrical, adding two similar diodes will yield this blue one over here, symmetrical trigger points, symmetrical limits. Having two different diodes, look at the difference between the triggers. They are not symmetrical at all. So trigger close to 4 volts, trigger closer to 4.5 volts. And a limit here at about 7 and a limit here at about 9 volts. Okay, and the triggers is dependent on the limits that you set. So you can get a non-symmetrical transfer curve. But typically you want something that is a bit more symmetrical. And even with the Zeners, you can still move this using an offset. Okay, the second output limiting circuit is to use a diode bridge with a Zener in the middle. So looking at the current flowing for a positive cycle, current will be flowing down here. Can't go that way, through the Zener, down to ground. Okay, so we have one diode drop, one Zener drop, and another diode drop. So that is our positive limiting. Our negative limiting, the easiest is to take the current flowing out of ground to make your head fit this correct, and it will flow through this diode, can't go that way, through the Zener, through this diode here, and into the source. So again, two diode drops, one Zener drop, and it's a negative. So there is your negative limit. Okay, again calculating resistor 3, we need enough current to supply our Zener and our diodes for them to switch on. Anything connected as a load and any extra circuitry attached as well as the feedback. And again, you pick the lowest resistor value, but this will be symmetrical, so these two will yield the same result. And there we have a nice symmetrical output with some limits. That is it for output limiting. So now I'm just going to open the simulations one by one and run them to show you. First, I opened inverting bistable here, and I set it up with a frequency. Let's run this. Here's our input, here's our output, and I designed this using two different resistors, so 1K and a 10K. So having a 1K here, we will have our switching at half of our limiting, so 4 volts, and the 10K will put us right here at 1 volt. Okay, so for those of you that don't know how to do a hysteresis of one of these, is you go to the time bar here and you right click, and here where it says time, you type in V bracket and whatever the node's name is. That's why I always give my names, and you want to plot it versus V in. So this will give you V in versus V out. Okay, so the output is on this side and the input is down here. So the blue one is with the two 1Ks and the red one is with a 1K and the 10K. And that is the inverting bistable. The next one is the same bistable just with offset applied. So I made an offset parameter so that I can have different offsets here, and the typical, let's make this minus 2.5, 0, 2.5, and 5 volts. And now we will have 4 different loops. One, the middle sitting at minus 2.5, one in the middle sitting at 2.5, the normal one where this is just a ground, and one sitting at 5 volts. So moving your trigger up and down using offset. So this leaves some room for digital integration if you want to put a DAC and have a movable trigger or whatever application you can find for it. Let's go have a look at our non-inverting bistables. So here is our non-inverting bistable. So the green one is our 2.2 kilo ohm resistor used here. So 2.2, 1 over 2.2 multiplied by our 8 volts would be the 4, and 1 over 4.7 would give us this one roughly at the 2 volt mark. So if we add a second one here, let's go with 10K, we will have a much smaller one there in the middle. There we go. So the larger you make this resistor, the narrower this trigger bandwidth will become. Okay, let's go and look at the one with offset added. So we added some offset here on the inverting terminal. Center at minus 1 volt, center at 0, center at 5. And so this also shifts the same as the inverting function. And I used the 10K here so to have a very narrow band. And let's make this 47K, and all the bandwidths will just change around the trigger limits that we set, like that. So let's go and have a look at our limiting circuits. So the first limiting circuit here is the inverting bistable, and I added a 4.7 volt Zener here, so this should be at, what's that, 6.1 volts as a limit. Let's run this, and our limit is set to 6.1 volts. Looking at the current here, this is drawing plus minus 10 milliamps. The Zener requires about 10 milliamps to work. Okay, so minus 10, and there is a couple of microamperes flowing into this feedback, and this resistor was designed with that in mind, and everything is coming through this resistor right here. Okay, so let's quickly do the bistable, and there we go, limit at 6.1, and the triggers here at roughly 1 volt. Well, not entirely, but we can tweak this narrower and wider till we are satisfied with our triggering points. There we go, that's closer to 1 volt. And we can use our cursor on this. Close enough to 1 volt. Let's go and look at the second trigger, second limiting circuit. For the second limiting, I have set up 2. Both of these should have a beta value of a half. So half of whatever the limit is will be the triggering point. And here is a 6.2 volt Zener, and here is a 8.2 volt Zener, so the limits here should be 6.9 and 8.9 volts. For this one, these are 4.7 volt Zeners both, so the limit here should be plus minus 5.4 volts. Let's run this and have a look. So that is almost 7, that is almost 9. Okay, so there's our 2 limits. This one, 5.5 minus 5.5 roughly. Okay, so that is clearly working correct. Now let's have a look at our hysteresis for the triggering points. There we go. So half times 7 is 4.5, and half times 9 is 4.5, sorry. So this is the one here, and half times 7 is 3.5. So this one over here, and 5.5 volts times 0.5 would be 2.5, 2.7 volts. So this is 2.7 volts roughly. Should be. Okay, so that is our triggers. So we can set different limits. We can set our triggers then, and our triggers will be a little bit more stable if we use diodes instead of just the rail voltages. Because here I can now change the rail voltages and this will still function correctly. In the other cases, if we change the rail voltages, our triggers will change. So adding limits is very important for these circuits, especially when we're doing square wave and triangle wave generators. They will be part of a design to include one of these, basically to stabilize the circuit output. Okay, thank you for watching.